name is Sinead McDonald, and I am a visual artist, and I am from Dublin. I have always been really interested in science fiction. Ever since I was a kid, I've loved science fiction. And most recently, I've been working with science as well. So I just finished an MA in fine art in the National College of Art and Design, and they do this mashup module there with University College Dublin, with the physics department in University College Dublin. And we were working on this, which is a Wilson cloud chamber, which is, I've become very interested in elementary physics and quantum mechanics and stuff. So basically, a Wilson cloud chamber is a fish tank, and you use alcohol and dry ice, and it makes electrons and cosmic rays visible to the naked eye. So this is a photograph from a Wilson cloud chamber, and these are just cosmic rays that are moving through the fish tank, and they ionize with the alcohol, and they produce these sprays like contrails. So while I was there, the Wilson cloud chamber is a very old piece of equipment. It's from, I think, the turn of the century it was invented. And while I was there, I was doing research into very early scientific equipment and physics equipment. This is the Malloy collection in University College Dublin. I'm not sure whether you can see it very well. This is where the postgraduate physics students hang out, basically. And it's all of these cabinets here is where they hold all of the very early physics and, natural philosophy equipment right from the very early 18th century. So I'd started to look at these. I basically fell in love with these machines. I mean, how could you not? But in this cabinet here, along the end here, most of the stuff has been catalogued. They moved to their present site in the 1960s, and they did a lot of cataloguing then. But there was a box that was there that nobody really knew what the machine was, and they couldn't kind of fit it into anything, and it was kind of badly broken, and I'll just show you now. This was the inside of it that we had originally found, and it was very badly damaged, and nobody really knew what it was. There were some papers and some schematics and stuff in the box as well. And it had basically been sitting in this crate since the college had moved to its present location in the 60s. So myself and two postgraduate physics students asked if we could sort of look into it and do a bit of investigation. We were given permission to do that, and we started to look at what it might be, what it might not be. The schematics and stuff didn't really give that much information on who had built it, but we did find this was on the side of the crate. I don't know if everybody can read that. It says 28A/FM, and according to the cataloguing of UCD, that means it was made in 1928, and the initials of the person whose crate it was FM. The only student that I could find at the time who was registered in the college was a Francis Meade. Now, Francis Meade had done work in theoretical physics around that time. He did publish a paper on Tommen's paradox, and I'll explain Tommen's paradox in a minute. He published a paper on Tommen's paradox and sending information back in time. Now, at the time, it was completely ridiculed. He was laughed at, basically. And he never published anything again. He was kind of basically never heard from again. I think he died in obscurity. We started to look at this idea of Tommen's paradox and to reference it back to the schematics that we found. I don't have any pictures of the schematics because the archive kind of whipped them off me when they realised what we were doing and wouldn't let me get them again. This is a graphical representation of Tommen's paradox. Now, if you can understand, I know there are some physicists in the room. I'm really horribly aware that there are some physicists in the room. I don't know anything about this, but I'll try my best. This is Tommen's paradox in a graph. And this is a lovely equation of Tommen's paradox. Basically what it is, there's an A and a B there. A causes B, okay? And T is time. And the idea is this is something called the Lorentz Transformation. So the idea is that A causes B, but if the velocity of A is faster than the speed of light, so that's the c squared bit, if the velocity of A is faster than the speed of light, then A actually happens before B. T becomes a negative number, and A happens before B. So it's this idea of particles moving faster than the speed of light and being able to break causality. So in Tommen's paradox, there's tachyons are the particles that were looked at. And it was actually theorized by Einstein and a few other people in about 1918, 1919, this idea of sending back information in time to an earlier version of yourself. So we started to look at tachyons in particular and how tachyons might transmit information, and how you might, first of all, actually, we looked at how you might be able to detect tachyons. Because tachyons are superluminal particles, they move faster than the speed of light, they can't actually be detected. But what you can detect is this, which is called Cherenkov radiation. Okay, so this is a graph. I know this is very sciencey and it'll be finished in a minute. This here, the kind of blobby sort of donut-shaped thing here, that's a tachyon. And you see the black line here is the observer. So the tachyon has moved past the observer before it can be observed. But what you get is a kind of a bounce back. So it's like when an ambulance goes past you or sonic boom. What happens is you get this reflection back, and that's called Cherenkov radiation, and that produces a very specific blue light. So this is an actual photograph of Cherenkov radiation. I did not take this. This is inside a nuclear reactor core. What happens in the case of water and nuclear reactor cores, so you've got energies that have particles that have an awful lot of energy because they're radioactive, basically, and they're sitting in water. Water slows down the speed of light enough that particles, supercharged particles, can actually move faster than it, okay? So that causes Cherenkov radiation, so you get this blue light that comes out of the water that's in nuclear reactor cores. So this is an example of visible Cherenkov radiation. But it's only because the particles are moving about in water that this can happen. So we thought, how could you detect this Cherenkov radiation in air or in a vacuum? So we thought if you got a CCD chip, I can't remember what CCD stands for, sorry. This is a CCD chip, which is a light sensor from a camera. It's in all of your mobile phones. There's a little one in your mobile phones. This is one from a Nikon SLR. So we thought if we got this and we put it into a vacuum tube, because it's in a vacuum tube, there's no fields that can mess with it, and there's no water that can mess with it. There's no anything that can mess with it. The only thing that can move faster than the speed of light in a vacuum is a superluminal particle. Okay, so a tachyon. So we thought maybe this would be a way to detect them if we tuned the CCD chip into a very specific wavelength and a very specific frequency of blue. So we had the glass department. TCD still have its own glass department, which is brilliant. So we had the glass department produce this, which is just a vacuum tube. They do actually still have uses. This is a vacuum tube which has the CCD mounted in it, and you can see it there. This is, I'm afraid to move up here at this stage, but this is the device here, and you can see the one with the black tape. So it's a light-proof vacuum, basically. So in theory, any tachyon particles, any of that shade of blue that's detected by the CCD chip has to have been produced by a superluminal particle. So that's how we figured out how to detect tachyons. The next thing though was how to transmit information with those tachyons. Anybody who has been following quantum cryptography might know a little bit about this. This is the spin. So every particle has a spin. It's got an up state and a down state. We started to look at the spin in particles, and we thought maybe that if you had a spin in a particle, that the up state could represent a 0 and the down state could represent a 1 in binary, and that maybe you'd be able to send information in binary this way. So we did a lot, actually, not me, John, who's a theoretical physicist, did a lot of experimenting with different wavelengths, and we did find that there was a kind of a weird pattern that was happening, but we couldn't make any sense of it. When we put it into binary, it just didn't make any sense whatsoever, and we were stumped, and we were stuck for about 3 or 4 weeks. So after we got stuck, we decided to go back to the drawing board, and I went back to the Malloy collection. And I was looking around at all the equipment again. I would quite happily die and haunt the Malloy collection. It's beautiful. This is something I found. There were a lot of broken bits of valves and all sorts of things in the box, but there were some of these little flywheels that we hadn't figured out what they were for. And then I saw this in one of the cabinets, and this is actually it's a receiver for Morse signal. So in the very early days of telegraphy, when you had more signals coming through, they used to hook them up to these machines, and the machines were like ticker tape. They had little tape things, and they would actually plot out the signal in Morse. And it quickly became obvious that actually humans were much quicker. It's one of the things in history that we were better at. Yay, go us. So these kind of became very obsolete very quickly when they realized that the telegraph operators were actually quicker than the machines at breaking the code, but they do still exist. So I thought maybe actually what we were looking at, we were looking for the wrong thing. We had kind of jumped ahead of ourselves in looking at binary, and then maybe it was Morse. So we decided to employ a little bit of kind of fiddling about. We got an engineer and a computer scientist from the University of Limerick on board. The computer scientist, when she had a look at the original box with all the valves and stuff in it, she realized that not only was there receiving going on, so with everything there's a transmitter and a receiver, and we'd sort of figured out that whatever this box was, that it was a receiver. There was too many amplifying valves and all that sort of stuff, so we figured that it was a receiver. But she had also noticed that there was some sort of calling for information as well, so it was kind of a transmitter as well. So we figured that it may have something to do, she'd found some light equipment, and she figured that it may have something to do with actually identifying people. So what we did was we hacked a flatbed scanner, and we hooked that up to the CCD as well. It was kind of handy. So we had the bar of the flatbed scanner run up and down and take a light reading of your hand. Okay, so that's what the hand shape on the top of the box is about. That information is then put up into the CCD. The CCD then transmits information, which is then translated, the information is then translated from Morse into ASCII, okay, because none of us knew Morse. And then the ASCII code then goes through the Arduino to a thermal printer, which is just a receipt printer. And the receipt printer actually prints out. And it was also calling for some other information, which we figured eventually was date information. So we made up this PCB, which just has rotary dials that puts in dates. So we had the machine working. The guys, the computer scientists and the physicists that I was working with just wanted to kind of put together an Arduino and leave it at that, but I'm an artist and it's all about the look. So I went back to the Malloy collection again, and I also travelled over to Paris. It's a great excuse. I travelled over to Paris to Arts et Métiers. Arts et Métiers, I don't know if anybody has ever been there. Again, it's another place that I'll quite gladly haunt. It's a museum that has all the sort of really old scientific equipment. It has the original Foucault's pendulum there, which is just amazing. You could stand and stare at it for hours. And write planes and all sorts of things. But I found these are early telegraph machines. And these are kind of from the war in France. I'm not sure whether they're First War or Second War, but they're a war anyway. So I just loved the aesthetic of it. I loved how the valves were still, like James, I like the blinky blinkies and the glow, and I think they're beautiful objects. So I wanted the valves to be obvious in the box. And yeah, so we started to play with it. I should say that we literally only finished like last week. This was a panic job completely. It was put together. Anybody you can look back at the tweets, this was on the floor in my house last week, still being put together. We haven't tested it an awful lot. We are getting messages back. Most of the messages that we're getting back are from at least 20 years in the future. So far, anyway, all of the messages that we've gotten back are from at least 20 years in the future. So we don't know if that's, because this is a receiver, we're assuming that there has to be a transmitter at some stage or at some time, but we don't know where or when the transmitter is. We also don't understand how Francis Meade, who was working in the 1920s and the 1930s, could have any concept of things like Cherenkov radiation. So Cherenkov radiation was only really pinned down in the 1960s. So there's kind of something weird going on with information being passed back and passed forward. But the machine is here. And it works. So you place your hand. Anybody who can come up, I ask for this stuff to be moved maybe during the break. Anybody who wants to come up and try it, you just put your hand down. There's a little scan button. The scanner runs, takes your information from your hand. Don't worry, it doesn't go to anybody else, I promise. Then you put in the date. So it's day, month, year, and then it prints out your future for you. So I'll just read this. So Layla did one earlier, and it has tachyonic anti-telephone report. On the 23rd of August 2056, you bite Sinead O'Leary in the face following a brief struggle. You're not sure why, you're not sure of anything anymore apart from an overwhelming need for brains. So that's the first one. Then this is one that I did during the break as well, so I just left the date the same. At 3 p.m. on the 23rd of August 2056, you are killed in a terrorist attack on your local meat mart. You're annoyed. This is your third death this month. Reintegration gets more expensive every time, and you still have to pay your mobile bill. So one thing I will say before I finish is that I've tried it a couple of times. Like I said, we've done very limited testing on this. I have tried it a few times where I've tried to put in the same date over and over again to see, and it gives you different results. So what we were thinking and what we thought at the very start was that actually, and it's something that I've discussed with the theoretical physicists, is that the possibility that once you read the future, that it can no longer exist, that it kind of collapses in on itself because you're aware of it. So this is something going back to loops and whether it's possible to change the future and stuff. So we think that that might be something that's happening, but we don't know. It was originally supposed to be called the Future Killer, but I was getting on a plane to London and I figured having a box with lots of wires and Future Killer written on it probably wasn't a good idea. So yeah, so the device is here. I'm going to, yeah, maybe we can get some extra space, and anybody who wants to, this can be played with. So anybody who wants to use it now, and then I'll hang about afterwards as well. So if you want to have your future read, and that's it.